So I'm actually making this as a kind of impromptu video. I recently taught a lesson on how to create a model from scratch. So this is going to be focused more on the data science part of my learning process, my learning journey. And I'll be coding in Python, and I have here a Jupyter notebook opened up. So for those who are interested in like data engineering and that kind of thing, what I'll be doing is creating the KNN, or K nearest neighbors regressor. So this is going to be the KNN, or K nearest neighbors regressor from scratch. Scratch spelled properly. Okay, so some rules. No dependencies, only using base Python packages, or base Python functionality. And that's it. So there are basically a few components to the K nearest neighbors, and I think I could probably show this a little bit here. So typically when we think about the KNN algorithm, we think of taking our training data and plotting it in n-dimensional space. And that's our training data. And when we take in a testing observation, we plot that, and we're looking for the nearest neighbors, and we're going to say, okay, what are our nearest neighbors looking like? What class do they belong to? And then we'll say, okay, well, we have the majority class is this one class, and then that is the class that is assigned that new data point. And you can transform this into a regressor simply by taking the K nearest neighbors, and instead of looking at the class, you look at the actual value, because it's a regression, so you have an actual number, a continuous number, and you just say, I'm going to take the mean of that, and that's going to be the prediction for that observation. So that's exactly what we're going to be doing here. So for each test observation. Okay, so the way we're going to set this up is to instantiate everything as a model, sort of like how sklearn does things. But again, we're not doing this with any dependencies, so we're going to have to keep our fingers away from any kind of package. So being mindful of that. So there are a few things we need to set up first. So let's talk about the setup. Okay, so let's start instantiating our model here. And I'm going to do a little testing down here. So let's do this here. I'm going to call this KNN Regressor. Okay, and we're going to do our init. And actually, when we initialize, I want it to say, this is going to be K, which we'll set at 5 by default. But we can do self K equals K. And that should be that. Okay, so when we instantiate, we'll say KNN equals a KNN regressor. And if we do that, we can say KNN.K, and we can see that, and it looks like it's 5 by default. We can set K equal to, the K nearest neighbors. We want K to be maybe 10, and that would be that. One thing I think is kind of ugly is like when you view the object by itself, it'll represent itself as the location, and then what the class is, and then it shows you the location in memory on the RAM. I don't find that to be very appealing, so I'm actually going to define my own representation, rep_r, and it takes nothing. It just needs to return a string. So we need to return a string. I'm going to return an f string. I'm going to use the class name, and I'm going to use double brackets to escape. And then I'll say K equals, and then I'll use brackets to say self.K. So this will be what it looks like in representation form. And I kind of like that. It looks a little nicer. Okay, so let's talk about our model. So typically, I'm going to go through like this process of fitting, like how you would normally do it. So when I normally create a model here, we instantiate, and then we'd like fit, and we would do knn.fit with some data, which is like x train, y train. That would be that kind of very typical. We currently can't do that, obviously. We don't have a .fit method, so let's quickly remedy that. Yeah, I keep doing that. That's one thing. I also don't have an X train or Y train, so let's actually make some data up for a second. So I think I'm actually going to, and well, I'm not being, so my model is not dependent on anything, but I can like quickly make some data up, I think. So let me just load some loading helper packages. This is okay, I'm not dependent on them. So I'm going to say from sklearn what is it called? Is it datasets? Datasets import. Ooh, what datasets do we have? Load. I need numbers, so I need a continuous sample. So I think Boston should be okay. So we load Boston. So this is just getting data. So this is loading data. So I think that if I do load Boston, that gives me a bunch of data. So it's the dot data. I think I can say return X. Yeah, that's true. So this will return X and Y directly. X, Y, bam. And then I can load my train test split, which you can technically do on your own. But I honestly, I want the model to be independent, but to test the model, I don't care. I just want it to work something quick. So I think this is model selection. Train test split. Yeah, okay. And let's loading data. We do our train test split. We will take X, Y. We will do a random state. So anyone who's following along could follow this. Equals. It's a variable that I like to usually put up here. Let's set that equal to 666 because I'm funny like that. All right, and that should be good. And this is going to be equal to x. And so now we have our data that is properly set up like that. And we still don't have a dot fit. Well, so when we do, I just need to like run this again. So there's a dot fit, but it doesn't do anything. So how does this KNN thing work? How does this algorithm work? So this thing is actually pretty dumb in terms of the fitting process. There's no real fitting. So when KNN has a prediction, when it's making a prediction, it is literally just taking, I'll show the picture again. It's taking the new observation, each new observation, plotting it in n-dimensional space with the training set, and just finding the nearest neighbors from that. So it just keeps the training set around in memory constantly, which is not the best, most memory efficient way of doing things, but that's what it does. So that's how KNN works. So when we say dot fit, what we're really saying is just keep this thing in memory. So I'm going to do exactly that. I'm going to say self dot x train with the underscore and set that equal to x train. The underscore just being a kind of sklearn paradigm where when you do dot fit and you create something new that wasn't there before, you put an underscore to signify that. Same thing with self dot y train, underscore there, and this is y train, and that's our fit method. So if I run everything again, actually let me move this up here. Okay, so we got that. The fitting process now has a dot. Look at that. We have a dot train set. The whole train set is in there. Perfect. Okay. Oops. So all train set is there. Okay, so we got something working. The next step in our algorithm, I'll kind of move this down, I guess, so we can kind of keep it in track of it. We have to make this Euclidean distance, so we need to make sure we have a way of calculating that. So let's actually set up Euclidean distance. So Euclidean distance is I to the squared power. So that's effectively the equation here. So we take the square root of the summation of the first feature minus the first feature in one observation minus the first feature in the second observation, square that, and keep summing those up. And you take the square root of all that. So it's, it sounds more complicated than it really is, honestly. So I'm going to call this thing Euclidean distance. And we'll put self, and it should take A and B effectively, whatever these two observations are. So I did mention that I'm not using any dependencies. So I'm not quite sure. Is there a math? So well, no dependency. I can use stuff from Python by default. So math is part of a package from Python that is default. So the summation of these things. So let me say the total equals 0. And basically I need to loop through both lists. So A and B are going to be lists effectively. Lists being the features of each observation. So I'm going to say for I, well, let me see. AI, BI in the zip of A and B. I could do that. And then I could say total plus minus these things minus each other. And then you take the square root of that. Then you sum that all up, and then you return math.square root of the total. I think that will work. So let me 0 to 3 and 0 to 4. So that's like, if you start at the origin and you go 3, 4, then the distance is 5. And that's what we see here. Okay, yeah, that makes sense. Okay, so Euclidean distance is working. Excellent. All right, so this thing is done. So let me just cross this out. Bam, done already. Anyway, k nearest neighbor indices outputs a list of indices of the nearest neighbors. Okay, so now we have to actually assume. So this thing, I'm going to just copy this. K nearest neighbor indices. So I'm going to actually just find that here. So this is going to take self, and it's going to take distances. And we need to sort this. Okay, so the process here is going to be, let's construct list with tuples with the distance first and then the index after. And I'm going to show you like why that makes sense here. So let's have a list here of tuples. Yeah, so it didn't care about the 99. It just looked at 1, 3, and 55, and the secondary thing didn't really matter. So it doesn't carry along when it does the sort. It just looks at the first element in the tuple. So that's what I'm going to basically do here. So here I'm going to call this the distances and indices. And I'm going to use a little list comprehension here. I'm going to use enumerate of distances, or distances. And I'm just going to say for I and distance in that, I'm going to create a tuple of basically the flip side, which is distance and I. Just a little list comprehension there. And then you just sort. So sort. Literally like that. That's it. And then I need to take, and then like I guess return the nearest neighbors there. You do that by looking at this. You slice it and you have self.k here. So this is what I'm going to use, self.k. Okay. So let's check that out. So if I'm given a bunch of distances here. Okay, so the first one, if these are distances, then 0 should be first, but it's the last index. So I'm looking for the indices specifically. Oh, actually, hold on, I'm doing something wrong here. So this should be, so I'm gonna keep it for now, but I'll show you like why it's not the same. So I got it sorted, and you see how the index is like kept along with it. Well, now I need to grab the k, which is 10. So let me make this 5 again. So, grabs the first 5 basically. But now what I need to do is reverse the process and just grab the indices, the second part here. So I'm going to use a little list comprehension here. So let me undo this, call this like, this is going to be k, distances and indices. So this is going to be, grab only first k. And here I'm going to return k distances, but I need to do a little more list comprehension. So for it's going to be distance. Well, I don't care about the distance, just the I in, and I'm going to return the I. Okay, so let's run that. And now I get the indices that I want. And believe it or not, we're basically close to done on this. Predict now is all we got to do. So, okay, so this works here. And now we do define predict. And you predict, you usually give it an x, some x value. So I'm going to call it, it could be x train, it could be x test, it doesn't really matter. It's just an x, meaning the features. And each feature is its own thing. So what I think I want to do is actually have a helper method called predict row, which takes a x row, and it does one thing really well. So let me pass for now. So what I want to do is, for each row, I want to make a prediction, right? So I have my predictions. And then, I think that's just a list comprehension actually. So I can just say return for x row in x, return self.predict row. I want to call it x row. Okay, because I like abstracting the fact that this is doing one job and I want to do it well. So with one row of data, then you can take the distances would be like another list comprehension. So for each, for one row, you now need to loop through all of the all the training observations and get the Euclidean distances for those. And that will give you your distances, period. And then you can use your k nearest neighbor indices to grab the test and make your predictions off of that. So this is a few steps here. So first, to predict our row, we need to get distances from given observation and all training observations. Then we're going to use this function that we made up here. So we're going to get target indices. Sorry, get k nearest indices using that thing. Now that you have the indices, we are going to get k nearest target values from self.x test, or sorry, y test, or y train, which was underscore. That's what we did when we did dot fit right here. This is the thing. So we stored our training targets as well. And then once you have those, we can just return the mean or return average, which is why it's a regression. Okay, so let's do that. These 4 steps are kind of like a lot, but it's very doable. So we now need to loop through for train row in self.x train underscore. We now calculate the Euclidean distance between it and the x row. So I'll just call self.Euclidean distance. We have our train row and our x row. And I will note that the order doesn't matter because the Euclidean distance doesn't really care because you're squaring. So you can put one first, it doesn't matter. This should give you your distances. Now that you have your distances, you can grab your k nearest neighbor indices. So this is going to be the k indices. And I'm going to call self dot this thing that we had before. Whoop. I'm going to supply the distances. So it gives you your k indices, and now we can grab our values. So this is going to be the average. So this is going to be values. So I want to append. I guess you could. So for index in k indices, you're going to grab the self.y train underscore, and you're going to grab the index out of that. And you return the average, you can just return, I guess you do sum values divided by the length of values. That gives you the average. That gives you predictions. So let me run this and see what we got here. So we can do our fit. We can do KNN.predict and provide our X train. We should get a list of predictions. Takes a while, but yeah, that's Okay, so we get a list of predictions, literally. Okay, so let's see how that matches up, basically. So now I have predictions, which is great. Now we need to actually score the darn thing. How do we do that? We have our last thing here. So let me undo this. R squared to assess. So let's talk about the R squared. So this thing is R squared equals 1 minus the residual squared so the sum of squared residuals divided by the kind of the total sum of residuals if you predict the mean, basically. So that's more like it. Okay. And how the heck do you calculate those things? This is bar, I think. Yes. So you take the total is basically looking at the variance, which is just the mean of y. Okay, so basically if we can recreate that equation, we have our R squared score that we can make ourselves. So let's do that, because that's where I am. Score self is going to take a, this should take the predictions, basically, right? So this is like y true and y pred. Okay, so first we'll calculate the numerator, it's the denominator, and then in the end we need to return 1 minus the numerator, which I'm going to call SSR model divided by SSR total. So I'll be creating those things here in the end. Okay. So for the numerator, we need to take the difference. Everything needs to be the difference in order, and then we square that and sum that up. Okay, so let's take the differences first. I guess you square each difference, right, before you do anything. So let's say for loop for yi y hat in, I'm going to zip y true and y pred. Yep. And let's say that you have a total for the model. Actually, I'm totaling this up anyway. So this is the same thing. That's equal to 0. And then I'll say SSR model is equal to these two things. And we're going to say you're going to be 1 minus another thing, and now you're to the second power, and that will be the total for the upper part. And we basically kind of repeat the same thing for the lower, except we now need the mean of the target. So we need one other thing. So this is y true mean. And again, we just do sum of y true divided by length of y true. Okay, I like to separate things. Okay. And we have a similar situation, except now we can like zip through this. We don't need to zip through it. I mean, we have the yi in y true, and we can say our SS total plus equals, and we're going to take the yi minus the mean, take that over that, and to the square root. And then that should be our R squared score. Okay, so let's see this thing working. So let's see, 2, 3, this should give us 0, or sorry, 1, because it's a perfect prediction. Our training and the model are, the model is perfectly predicting, so that should give us a score of 1. What if we have a bad model that has that's way off? It should give us a very low score. Yeah, so that's worse than the baseline model, which makes sense. I think there's one issue. If the baseline model is perfectly good at predicting, we get a 0 here. So this becomes a 0. So I think I'll do a try. Except here, where I will return 0. return a float. This should be float because everything else is going to be a float. So if I can't return that, I will return 0 by default, just to prevent that situation from happening. Yeah, so I got a 0 here. Okay. All right, so we can now predict with we can now score our model. Actually, we need to do that. So this is the R2 score, but I need to actually have a method for scoring. What the heck? Okay. Let's go back up here. So let's go here. So that is done. And now we have, typically we have a dot score method. So I'm gonna actually make that out real quick, where you get in your X and your Y true. That's usually how that goes. So this dot score is just going to have the model itself do its own prediction and scoring. So let's get preds equals self dot predict on X, and then I will return self dot R2 score. And we're doing R2 score on the Y true and the preds that we just made. That should be, it should be able to return its own score. Okay, so let's think about this. So we got this. We got KNN dot score X train Y train. Not so good. It's a little less. So maybe we can change our K to be like 10 or something. See how that works. Not the greatest, but you know, that's that's KNN for you, I guess. So let's see how this stacks up actually. So right now this is an implementation that required no imports or anything. It's just basically just using math, just so. And of course, we could always implement our own square root function if we really wanted to. In fact, I think, now that I think about it, yeah, I can. I'm being dumb. You can just do square root of 0.5. You can just times it by 0.5. That's the square root. So now I don't even need the math function. Fantastic. I think this still works the same. Nothing broke, right? Okay, cool. So let's think about this in terms of how this compares to sklearn and the way they do things. So let's import that actually. So KNN, just take some parameters. So let's see what we got here. We have n neighbors, so we'll set that to 10 just like we had before. So I'll do that here. So I'll say n neighbors equals 10. I will note also that we're using the metric is not Minkowski, we're using the Euclidean. So we're going to set that to, so the metric is Euclidean, because that's what we're using. Okay, sknn dot fit, we're fitting use X train and Y train. Okay, so that's that. There's the sknn dot score, sk this and that. And it looks like it's exactly the same. So, and I'm like comparing the scores now. If I pull these up, it's hard to tell. I don't think there's much difference, if any. Let's see. It's a little bit actually. Yeah, this is a 5538. Oh no, actually they rounded. I see. So actually mine's is slightly more precise. And this one is 23699. Yeah, this one got. Oh, now theirs is slightly more precise. So excuse me, but there's not very much difference between the two. So it looks like we've successfully implemented a from scratch model, the KNN Regressor, using a few pretty straightforward, fairly straightforward methods. Hopefully that wasn't taking too long, but I think I can share. This as its own repo, I guess. So I'll share this out so you all have it. But hope that was helpful. This is definitely in line with my my journey into data science. So if you find this kind of thing useful and informative, please do not be afraid to leave a like, subscribe, all the good stuff, and I will see you next time. Take care. Bye.